Hello, it's David from David Savoury Electrical Services Limited, and hopefully you're doing better than me in dispelling the old Christmas and New Year hangover. Anyway, a surprising video this. I had no inkling I'd be making until I woke up this morning and boffed one off in the shower, but then one does find that some quality time on one's own with the loofah and or the loo roll often gets the old grey matter waking up and standing proud. And today's topic, which came to mind just in time to ruin the money shot, was the subject of capacitance and its sometimes unwanted effect on LED lighting. But allow me first to give you a demonstration before we talk turkey. Don't mention food. Okay, I have here a General Electric R50 LED lamp circa 2011. Jolly good. I also have here a presentation converter. Nothing special about this, there's no electronics inside there. It merely converts the E14 screw fitting to a B22D bayonet, which allows me to mate it with my button lamp holder up here. Now, hang on to your socks and watch this. Power on, RCD on, light on. No surprises there, right? Light off, and indeed it's off. Now watch what happens when I switch on this unrelated socket outlet circuit, this circuit serving this socket down here. Can you see that? Should we zoom in and turn the light off a little bit? Alexa, turn off the desk lamp.
Okay.
Whenever I turn on this socket circuit, you can see a glow from my LED lamp here. Surprising, eh? What the ruddy hell is going on here, and what can we do about it? Well, I have 4 reasons for this phenomenon and 3.5 potty-mouthed answers, so stay tuned, or if you're easily offended, you can bugger off. If you want a profanity-free answer as to why your Swish new energy-saving LED lamps are all aglow when they're supposed to be off, it's already too late, but you can still check out the link in the description, which is to a free advice article on my website, written nearly 6 years ago, that explains it more politely. Still here? Well, I thought you would be. Unfortunately, this is why I don't write so many articles for my website anymore. Nobody wants to bloody well read them, at least not when they can watch it all in TV form, even if the language is a little blue at times and the presenter has a crap haircut and vomiters down his t-shirt. The aforementioned webpage, rather surprisingly, is the most popular on my website and has been for a few years, attracting, as it does, hits from all over the world and even the occasional international thank you, which is nice and gives me a warm glow around the stones. So without further prevarication, let's cast a glance at what's happening and why. And we'll start with cause number 1, as that's the most exciting: unwanted capacitance. Yes, indeed, this is rather exciting, as I'm already demonstrating this on my impressive sounding simulation rig, which is admittedly less impressive when you realise it's just an old CU and some accessories plopped rather half-heartedly onto this wall. No matter, suffice to say that this has appeared in a number of previous videos and isn't meant to represent an ideal setup. Indeed, there are a number of issues with it by design for the purposes of my producing video blarney such as this. A quick look at what I've got going on here then. We can ignore these 2 socket circuits which form a ring, because that's nothing to do with today's shenanigans. Instead, we only need to concentrate on 2 circuits. This one here, which is a lighting circuit, as we've seen, powering this button here, and we have a socket circuit, which is a radial that serves just this outlet here. Now, I've mentioned in at least one previous video that this grey box to the left contains several meters of wiring so that I can get some impedance numbers that aren't a big fat 0 whenever I do perform R1, R2 or ZS testing on this thing. And if I take the lid off, then we can indeed see an excess of multicolour mess. Domestically speaking, normally your wiring would be self-contained for any given circuit, so the line, neutral and circuit protective conductor would be grouped together in a single sheath, such as in a flex, or for fixed building wiring in the UK, a twin and earth cable like this. Of course, singles, as found in conduit wiring or in its double insulated form on older UK installations, are a different kettle of fish and can potentially see line and neutral snaking around the building separate to each other, which isn't ideal. And to see why, here I have separated line, neutral and CPC for both the radial socket outlet and for this lighting point. And I then tape together the wiring for each of those circuits. So line for the socket is taped to line for the light, same for neutral, same for CPC. In effect then, this simulates the lighting and socket circuits here following the same route, but each with their line taking a different path to their neutral, as it may do in an older installation or in one wired by an asshole. So the 1.5mm wire for my lighting comes from the breaker, it winds its way around the gaff and goes to the light. The neutral then comes down, follows a different path and goes back to the neutral bar. The 2.5mm wire for my socket circuit comes out from its breaker, follows the same roundabout route and ends up at the socket here, and again the neutral from here comes back, winds around a different route and ends up back at the neutral bar. And we've seen that when I energise that socket circuit, it has an effect on the light. The light is illuminating with a bit of a nuisance glow, a glow that should not be there. And I bet you're thinking it's something to do with electromagnetism, huh? After all, we all know that a current travelling down a wire creates a magnetic field. Only there is no current. Remember, this 2.5mm line wire is only going to this socket. So it's presented here at the live prong hole when the socket is on, and it's not at the moment, it's switched off. The neutral is winding its own separate way around and appears on this prong hole on the left here, but this socket contains no internal load such as an indicator or USB charger, so with no load connected via a plug top between these 2 points, there is no current flow along our wire, and therefore no magnetic field. That said, we know the socket wire is energised as we can see it physically switched on here. There's 230 volts AC on this socket's 2.5mm brown wire looped here, although not on the 1.5mm lighting wire taped to it, as the breaker for that circuit is off. I can show that the socket wire is energised with this, a non-contact voltage indicator. These come in many forms, this one being a Q-Tech Q-Stick Duo with a rather pleasing two-tone toot, although a fluke volt alert is the one I personally tend to tote on the tool belt. With this socket circuit off, my non-contact indicator indicates the fine end of fuck all. However, when the socket circuit is powered, I get an indication. A good 15 or so centimetres away. So if there's no current and no magnetic field, just what is this thing detecting, you may well ask? Well, it's picking up an electric field, and to understand electric fields, we need to know more about how a capacitor works. A capacitor comes in a variety of values, types and form factors, and they basically consist of two conductive plates separated by an insulator called a dielectric. As far as DC current is concerned, a capacitor is a dead end. You can send a charge onto one plate, but the insulator prevents it passing to the other plate. In AC, however, because of the changing sine wave being applied to it, a current can pass via the electric field, which develops across the dielectric. You can do your own research into capacitors. I'm certainly no authority on electronics, so look at channels such as Big Clive or my personal favourite SDG Electronics, as linked in the description. So how do the basics of a capacitor apply here? Well, I said that a capacitor is two conductive plates separated by an insulator, and what we happen to have here is an energised copper conductor on the 2.5mm socket wire, a dielectric insulator formed by the PVC insulation and an air gap, and a conductive antenna in the tip of the non-contact voltage indicator. We have therefore created a capacitor between the energised wire and the non-contact indicator, and a tiny current can pass through the electric field of that capacitor. All we need now is a path to earth for this current to get to in order to complete the circuit and allow the electronics inside the non-contact detector to give a visual and or audible indication that voltage has been detected. Well, where's that path to earth then? I'm the path to earth. Yes, my body is forming another capacitor, that from the non-contact detector down to earth. So the minuscule current traversing the electric field between the wire and antenna passes in the same way through me to earth. I am capacitively coupled to earth. Earth being the floor I'm standing on as though it's the plate of another capacitor. The dielectric between me and earth being my DeWalt ball kickers and Christmas socks, and my body being the other conductive plate of that capacitor. Now you may say that my standing on this wooden floor doesn't make for much of an earth, and yes, I may not be planted in a muddy puddle in direct contact with the ground, but nonetheless there is a potential difference between down there and the 230 volts AC up here, and if I really wanted to prove that, I could grab hold of this live buzz bar and you could watch my hair stand on end and liquid shit pour out of my arsehole until such time as the RCD decides to kick in. But I don't earn enough from YouTube to want to demonstrate that personally, so I shall leave that to your imaginations. You're imagining it right now, aren't you? Wait, I didn't say I was naked, you perverts, although thank you for picturing the long schlong. Here is a demonstration of how I am part of the non-contact circuit. For those watching who already do site work, how often has this happened to you? You have an energised wire and you want to go back to the board to clock off the breaker, only you don't know which breaker it is. As an audible aid, you want to leave your non-contact detector next to the live wire so you can hear when it stops sounding. So you balance it by the wire and you get it tootling away and then you make to leave. Oh, will you look at that? It's right next to a live wire, but it's showing dead. That's because it is no longer capacitively coupled to earth through me. If I place my body near it without actually touching it, then once again a capacitive link is formed between it and me, and the current can flow through me to earth, and the indicator indicates accordingly. Fucking magic, eh? To get this to work without my presence, I need to couple it to earth via other means, and of course I can use one of the CPC wires that's right here and is a better path to earth than I should ever be. If I reorientate this so that the antenna is near the live wire and the base of the thing is near a CPC, then I can happily walk away, as it's now capacitively coupled between line and earth without my presence. And it will continue to sound off reliably until I clock off the power. And this is one of the flaws with non-contact voltage indicators and why such cannot be relied upon for safe isolation. It only picks up a live wire if it itself is capacitively coupled to earth, and its efficiency is affected by how the person holding it or the location it's placed in has been grounded. I should also mention that one with a power button and active indication is better than one without. The Q-Stick Duo has a visual and audible heartbeat to let me know it is on and active, but the Uno model has nothing. The Uno model simply lights up when placed near a voltage source. But if the batteries are flat, then it won't work, and I have no way of knowing if that's down to a flat battery or because the wire I'm testing is dead. I have to place it near a known live source to verify it's working in the first place. But anyway, I'm going off topic. Suffice to say that non-contact indicators are useful as indicators of a voltage being present, but are not suitable for proving dead, as they are fallible. A quick aside before I get back to topic, and my TIS-859 that I showed in another video has itself got an electric field detector function, this EF button here, and if I hold it down then we should see EF appear on the display. Jolly good. Okay, now if I bring that closer or further away to an electric field, then it should give me an audible and a visual bar graph indication on the display here of the strength of that electric field. So if we turn our circuit off and switch on the EF function here, and you can see we've got nothing. But if I turn the circuit on, then as I get closer to it, the tone gets more rapid until I'm right on top of the sucker. Jolly good. All very well, and my apologies for blabbing on to all those who just want me to get to the bloody point. And indeed, what the hell has any of this to do with our nuisance glow, you may well ask? Well, I've demonstrated that my 2.5mm socket wire forms one half of a capacitor. My 1.5mm lighting wire running alongside it naturally forms the other half of a capacitor in much the same way as my non-contact voltage indicator did. We have the 2.5mm socket wire with its energised copper core, we have our 1.5mm lighting wire with its non-energised copper core, and we have an insulating dielectric between them, namely the PVC basic insulation and a bit of an air gap. Our wiring, when running this way, forms a capacitor. Between the 2.5 and 1.5mm conductors over the several metre distance of this cable, a tiny current is passing. It's flowing from the socket breaker down into the socket line wire, through the electric field created by the 230 volts AC on the socket line wire, and into the adjacent wire of the lighting circuit, where it then causes the sensitive electronics in this particular lamp to actuate with a visible glow of the LED elements as the current passes through the lamp to get to neutral. Now, this phenomenon may have been the case with your house wiring for years. It's just that you never noticed it until now, because the current here is so small that it had no effect on the incandescent or fluorescent lamps employed before. Even LED lamps will react in different ways depending on their design. Here I have a Tesco R58 LED lamp, and if we take our glowing GE lamp out and put the Tesco one in, we'll see how that current affects that. And there's nothing, no nuisance glow at all, and that's simply because the Tesco lamp has a different circuit which is not affected by this tiny capacitive current. Let's see if we can take some readings of the voltage and current on our glowing GE lamp. First, let's see what current we get, and I'm using my TIS 560 clamp on the 2mA scale because this is the most sensitive clamp meter I've got. And when I reviewed it a couple of years ago, I questioned where I would ever use the 2mA scale. Well, shut my mouth, because here we are. I've got it around the 1.5mm lighting wire here, and we can see we're reading 0 at the moment because the socket circuit is not energised. If I switch that on, I can confirm that my light is glowing, and we're picking up a reading of 0.003 milliamps apparently, which is 3 microamps. That's rather piffling, isn't it? Can that really be enough for these LED elements to glow? Well, it seems so, unless I'm cocking something up, and let's face it, I may be, but we can physically see the effects here, and unless this is some kind of flat earth fake news, and you certainly shouldn't believe everything you see on YouTube, but it's easy enough for anyone to recreate this experiment and produce a proper video if so minded. Okay, I've opened up the lamp holder, and we can see that our lamp is still connected and still got its nuisance glow about it. I've also installed a couple of copper prongs here, copper legs, in order that I can connect some voltmeters to. So let's see what kind of voltage reading we can get out of this, and we'll start, I think, with my Clive CL2300A. So it's on the voltage setting, and if I connect it, it gives me a reading of, how well can you see that? 70.8 volts. Okay. Next, let's take a reading with my TIS E217. This is a new meter that I've obtained. I haven't had much of a chance to play with it yet, but I might do a new Toy Tuesday on it, and also my TIS E247, which is another one that's come my way. But we'll take another voltage reading, this time with the TIS. And I quite like this. It's got a really nice backlit display, hasn't it? Let's just connect that up then. Now we saw 70 volts on the Clive. On the TIS, we're getting 98.8. That's interesting. Let's break out the big boys, shall we? We've seen what the multimeters say. Let's see what a multifunction tester says. So we switch that to volts. Oops. Connect that up, and we get a rather unimpressive 3 volts. Okay. Quite the range this, isn't it? One more. Let's fire up the Metrel MI3100S. Switch the voltage. And the Metrel says 24 volts. Bring that closer. 24 volts at 50 hertz, so it's giving us a frequency reading as well. Quite an array of readings. So what the Mary Poppins is going on with this thing then? Well, to be honest, I don't know. My assumption is that these different testers with their different chipsets and probe impedances are each squashing this induced voltage as they try to read it, and as it has no real meat behind it, you're getting some differences in readings. You'll notice also that merely connecting any of these voltmeters extinguishes the light. If I disconnect this, it comes back on. So just connecting a voltmeter to it causes the light to stop glowing, which is interesting. Let's run with the TIS E217 then, because that gave us the most impressive reading, and it also has that nice backlit display which hopefully shows up on camera okay, kind of. So I'm going to connect that, and of course as I connect it the lamp extinguishes and we get this reading of currently 98.9 volts, 99 volts. Can the camera see that? I think it can see it. Okay. Now, if this is down to capacitance, then I should be able to improve the, albeit unwanted performance of my wire capacitor by squeezing the wiring, as that will reduce the dielectric insulator by closing the air gap and pinching together the plastic insulation of the two wires, thus reducing the size of the electric field the current has to cross. So if I squeeze that now, we should see our voltage. Yes, look at that, it's gone up to 115, 116 volts. So I'm improving the operation of the capacitor, and I can actually see the light is starting to light again even with the voltmeter connected. I don't think the camera's going to pick that up terribly well, but I'll see what I can do. Can you see that coming on? Probably not with all the lights on in here, but we're improving the performance of this thing enough that the voltage is going up and the current is increasing and the light is able to glow a little brighter. In fact, if I disconnect the voltmeter so that the light is on, then if I squeeze it again, I'll try and hold this so that you can see it. Again, I don't know how well it's going to pick up on camera, but the light is glowing brighter as I squeeze it, very slightly, not by much. Now, I should lay a disclaimer here and say that handling energised wiring with only basic insulation is not advised. A single insulating layer is the last thing to prevent you from being fried, and I shouldn't be squeezing this stuff in this way, as any flaws or breaks in the PVC could see me zapped. So although I'm bravely attempting to prove a point on this video today, do bear in mind that I am professionally hungover. So even if the voltage across here is as high as 101 volts as it's showing there, I've already shown that the current is tiny, sod all, and that even the connection of a voltmeter seems to squash it. Therefore, I should be able to, if I disconnect that, I should be able to touch between the 2 points here quite safely with no ill effects. And indeed, let's do that. If I touch between line and neutral, you can see the impedance of my body is shorting out the light, but I feel nothing. Just a slight tingling in my balls, but that's only down to impure thoughts and is quite unrelated to this experiment. How then can we ensure that stray capacitance doesn't affect our LED lighting? Going back to something I said earlier, we can ensure our line and neutral wires are grouped together, i.e. in the same conduit or sheath, as this will null out the electric field. The neutrals of my sockets and lighting circuits and the CPCs are here following a different physical path to the line wiring, but if I bring the neutral close to the line wiring, you can hopefully see on camera that as I get them together the light is physically dimming a little. Let's connect to the voltmeter, shall we, and have a closer look at quite what effect it's happening. Oops. So we'll stick the voltmeter on here, and we're reading our nearly 100 volts, and if I introduce the neutral to the line wiring, we can see it drops down. We're down to 95. If I bring the CPC in as well, then we're already down to 86, 85. I'm never going to get it down to 0 because we still have this capacitive effect going on here only by running these cables so that each circuit is, the two circuits are separated out from each other. Will I get it down to a 0 level and completely eliminate the problem? But you can see that the electric field is diminished by the proximity of the circuit's neutral and CPC to the line wiring. Indeed, this setup is imitating a TNCS arrangement, so neutral and earth are connected together at the head. At the consumer unit, there's no potential difference between them. Even with a circuit energised and passing current, it's quite safe for me to touch between neutral and earth without any ill effects. The only difference between them, of course, is that the neutral is passing through the RCD. Because neutral and earth are grounded, stray capacitive currents get squashed and can't leach into neighbouring wires or loads if line, neutral and the circuit protective conductor are grouped together throughout their run. One thing about my test rig, which will probably differ from what you're seeing at home though, if I turn my light switch off, then my nuisance glow problem goes away. For most people, turning the light switch off is when the problem shows up. That's okay, the principles are the same, it's just that the capacitance is happening on your switch wiring, probably because it's long and or it's 2 or 3 way. It runs along or near a source that is creating an electric field, and switch wiring often contains no neutral, and on old installations perhaps even no CPC to dampen the effects. Here, my switch is adjacent to my lamp holder, so it was more practical for me to introduce the volt onto the feed wiring to demonstrate this today, but out in the world it will mostly occur on the switch wiring. Jolly interesting stuff, I'm sure you'll agree. So, short of expensive rewiring, what is my top tech tip fix for this? Well, it's easy enough, but don't attempt it unless you're savvy with the screwdrivers. I've shown this is just a stray voltage with no real current behind it, and it just needs a bit of mopping up, and we've already seen that a parallel resistive load such as my voltmeter or even my hand will make it go away. So let's put such a load in place, one that costs nothing to run and will cope with either the capacitive voltage or the full mains voltage when the light is on. This is a neon indicator. I have an Amazon link to such in the description, although this particular one has been removed from a defunct electric shower. If I connect this between line and neutral, then the resistance of this indicator causes the lamp to extinguish and the indicator to faintly glow instead, as it sucks up the waste current. This indicator is small enough that it can be lost above the ceiling or behind the light fitting. When power is restored to the light circuit, then the indicator glows brighter, but if it's positioned in such a way that you can't see it, then it doesn't really matter, does it? So let's put that on. Super stuff. Now, if I switch on my socket circuit, you will notice that the LED light is not on, and the indicator is. I don't know how we're going to pick that up. Let's turn the lights off again, shall we? There, can you see that? That little faint glow. Now when we put power onto the light, you can see it glows a lot brighter, but again, it's small enough that it can be lost within the fitting or above the ceiling or whatever. You can stick it on the end of a string of downlights, or you can stick it inside the light fitting itself. It's not really going to cause too much of a headache. So there we go, that's the way to fix it if the problem is capacitive. Cheap to buy, easy to hide, lasts for years and costs nothing to run. If capacitive induction is your problem, then consider it solved. Just make sure the neon indicator you source is suited to the voltage in your territory. Let's move on to problem number 2, which is smart switches. Recent years have seen an explosion in smart technology, with many people retrofitting smart light switches onto wiring whose designers and installers never envisaged such wizardry being invented. So what's the problem? Well, your smart switch has a little electronic brain. It may be a relatively simple one, such as in this touch dimmer that I've now put up here, or it may be something that communicates with your phone or voice controller spy tech of choice, in which case it probably has more processing power than NASA ever possessed, heading to the moon back when skirts were mini and Beatles were big. To demonstrate, let's show this touch dimmer controlling this Philips dimmable LED lamp, and we can certainly dim it down and we can dim it up. All jolly good, and now let's turn it off. Oh dear. Now, it's all very well having a clever little circuit inside your light switch, but nonetheless it is a circuit, and my school physics lessons taught me that a circuit needs to be complete in order for current to flow. I mean, if there's a PCB inside this thing, then I can't just connect it to positive and not negative, or to line and not neutral, because I need 2 points with a potential difference across them for a current to flow across the circuit and make great things happen. So if there is a PCB in here and we've only got a permanent line in and a switch line out, then where does our clever chipset get its damn neutral from in order to power up, talk to your iPhone and set the moody light level when you cuddle up to your better half and select the Netflix and chill mode? If we break it down into a diagram, then we can see that the switch electronics does have access to neutral. It's just that it has to pass through one or more lamps to get there. In the case of incandescent lamps, these are just resistors. I mean, that's how they work. The resistance of the filament opposes current flow, which generates heat, which generates light. That's a wholly inefficient way for a traditional lamp to work, of course, as the light produced is actually a byproduct and most of the energy is wasted as heat, but that's how it works. Our smart switch therefore passes a small control current through the lamp, or lamps if there are more than one, in order to power up and operate, and that smart circuitry needs 24-hour power, as these things are on even when off. That is to say, the circuitry inside them is always on and waiting for the command to turn on the lights. Yes, smart switches are always awake, even if you and your light bulbs are not. But while incandescent lamps are all largely made equal, we've already seen today that LED lamps are not. An LED element itself typically only requires 2 or 3 volts of DC to operate, so to make a lamp which is bright and can run from 120 or 230 volts AC requires some kind of circuitry. You may have a string of LED elements connected in series to divide the voltage, with the 2 separate strings, one powered from the positive side of the AC waveform, the other from the negative side. Those are the lamps that flicker horribly and fail as soon as any one element pops. You may have DC rectification with or without regulation to drive a smaller number of higher power LEDs. You'll have different circuit designs, different specifications, different components with variances on component quality control, and at the end of the day, lamp A from Acme Corp will be designed and manufactured completely differently to lamp B of Scheitholer of Shenzhen, even if they are physically similar and glow in about the same way. So far as smart switch manufacturers are concerned, all bets are off if you're not using lamps that they have themselves tested and verified as being compatible with their kit. If you use a different brand of lamp and the control current for the switch passing through them to get to neutral is enough to actuate the electronics, causing a faint glow, then there you are. Simply replace your LED lamps with models that your switch manufacturer has tested and confirmed to be compatible, or change your switch. And you know, I had this myself a couple of years ago with a client who bought some shite smart switches which would only work with the lamps produced by the same brand. We tried all sorts of other makes of lamp, and Nuisance glowing was the result. A fair old bucket of monkey balls, I'm sure you'll agree. But there you go, LED lamps need to be matched to smart switches or dimmers. Speaking of dimmers, problem number 3 is down to dimmer switches. A touch dimmer such as this Hager model, which controls the light electronically rather than via a mechanical push, may have a minimum load requirement, in this case 60 watts. And if your efficient LED lighting doesn't meet that load requirement, then you can expect gremlins on your lighting. You may need to change your dimmer for one specifically designed to work with LEDs, such as this Vari-Light V Pro. The V Pro has no minimum load and is also programmable, so if your LED lamps aren't playing properly with it, then you can set it to a different driving mode which may be more compatible. Switching your switch to one that is LED compatible may be the answer if your existing switch predates LEDs and is anything other than a straight mechanical on-off affair. Reason number 4 for unwanted LED lighting glowage is down to our old friend insulation resistance, or rather the lack of it. Our live wires are covered with plastic to keep us from getting zapped, but that insulation also keeps our circuits separate when cables follow the same wiring route. Should that insulation be damaged or compromised, then it may be possible for current to leak from one circuit into another. We've already seen how a small current can form across an insulating layer through capacitance, but with an insulation breakdown, a much larger current can flow, and in the event of a breakdown to the point of a dead short, then one circuit can end up wholly powering another that it isn't supposed to. Allow me to demonstrate with the use of a demonstrator tool I have built specifically for the job. This is the Billy Bollocks insulation resistance demonstrator. We have 2 cables from 2 different circuits running along here, but look, Joe Homebase, the DIY disaster, has only got to put a bloody screw in the wall and caught them both. We can see that this screw has caught the line wire, the brown wire of each cable, but if I connect my metal tester to the brown wires, while it's in continuity mode, I can confirm that it is open circuit. That is to say, the screw is not in direct contact with the copper cores of these cables, and there's no resistive path between them via the screw itself. The screw has damaged the insulation though. It's eaten through the outer grey sheath and into the brown PVC protecting the line cores. Now, although there's no path through this screw when dead, Let's see what happens when we start pushing an electromotive force into these cables, which is what would happen if I were to switch these circuits on. My metal is going to pump in 250 volts DC on the brown clip, and if these cables were undamaged and in top condition, then nothing would come back on the green clip and we'd have a reading greater than 999 megaohm, which is off-scale high for this instrument. Let's see if we do get that. Nope, that's a fat fucking zero if ever I saw one. What's happening here is that when the 250 volt goes up this brown wire, it has enough welly behind it to be able to jump the small air gap between the copper core and the screw where the plastic insulation is missing. It also has enough welly to jump the air gap from the screw into the second cable, as it too is missing its plastic insulation. It then travels back down this brown wire and into the tester, which reports the failure. Although it's open circuit on a dead test, it effectively goes short circuit when powered. If cable A goes to our lights, then we'd be seeing them illuminate whenever cable B is powered, as we have a leak between these two circuits. Now, although my insulation resistance read as 0, out in the world it could be anything, and if it's anything less than a megaohm for a 230 volt circuit, then it doesn't comply with BS 7671, and funny things may start happening. The only way to have this kind of fault fixed is to hire a proper electrician with the right kind of kit and enough noughts to track down the fault and put it right. So that's my 4 reasons for unwanted glowing of LED lamps: stray capacitance, smart switch incompatibilities, dimmers with high minimum load requirements, and insulation resistance faults. As for hangovers, my recommended cure is hair of the dog. Chin chin.